So our next speaker is David Chisnell, who actually started with us in 2012 working on the C compiler. Well, he did the original Cherry C compiler and really helped develop the Cherry architecture as we see it today. In 2018, he moved to Microsoft Research down the road and set up the Cherry Up project and led that for quite a while. And now he's left and is involved as a startup. So he's director of systems architecture. I had to read that bit. At SCI Semiconductor, that is aiming to ship Cherry-Ut as a product. So over to David.
Thank you, Simon. And Simon said there are 3 great speakers for this session, and there are 4 speakers, so I'm assuming I'm the 4th one. So I wanted to talk about supply chains, partly because I always want to talk about supply chains, but partly because supply chains are really topical at the moment. We very narrowly missed a supply chain injection compromising SSH in all Linux servers. And so how many people have read excruciating amounts about this vulnerability? Okay, so I'm going to skip through how it worked very quickly. And I'll start with what should have happened. So when you're running a dynamically linked program, the runtime linker is loaded. It looks at the program binary. It recursively goes and finds all the libraries that depends on. It maps those. And each of those may reference symbols in other libraries. And so there's a global offset table for each one that the linker then populates. And there's a really nice security feature called relrow, which says, once you've applied these relocations, mark all of these things read-only. And the problem with that is to be able to mark them all read-only, you have to eagerly resolve all of the symbols, even the ones you're not using. And in libLZMA, the library that had the exploit injected into it, there was a symbol that wasn't used, but which has an ifunc resolver. And ifunc is this performance feature that says, so I've shipped 10 different versions of a function in my library, and I'm going to do some dynamic runtime introspection to pick the one that will be fastest for your particular CPU. And then it tells the runtime linker which one to put in, whichever GOT entry should be referring to that symbol. And that ran early on before any of this relocation, or any of these GOTs had been marked read-only. And rather than just returning the thing, it went and poked some data structures in the runtime linker and found a place where it could inject a control flow hide the SSH binary itself. And then very bad things happened. And so the obvious thing we should think is ifuncs, let's just not have those and the problem will go away. But ifuncs were just a convenient way of triggering this exploit. They're not the underlying problem. Any library can run arbitrary code when it starts up. And normally that happens after the GOT has been marked read-only. But unless you've got OpenBSD style monotonic read-only transitions for page mappings, all it needs to do is just call mprotect and change the GOT back to being read-write and patch the thing. And then the same exploit could have worked without hijacking ifunc. But okay, so we can do that, make the memory immutable thing. And then all we have to deal with is the fact that when we run that untrusted code, it can fabricate addresses and it can tamper with arbitrary data anywhere in our program. And even compiling things for a Cherry PureCap ABI is not sufficient to address this, because that global constructor will run, there'll be some garbage on the stack. Maybe you can walk up the stack and find the ELF auxiliary arguments, and then you can go and find a load of other things. There are lots of ways that you can chase pointers to go and find things. That Cherry is great as a defense, and Cherry by itself, just recompiling for a PureCap ABI, prevents a lot of things that would lead to arbitrary code execution. But once you have arbitrary code execution, you rapidly find that actually a lot more memory is reachable than you want. So on a current system, how do you reason about this kind of thing? If someone says, oh, we've discovered there was a supply chain vulnerability in this library that you link. How do you say, well, what damage can that do? And at the moment, what you say is, well, I guess that library can do anything that my program can do, and my program runs with all the rights of my user, so it can't modify system settings. All it can do is leak all my personal data and destroy all my personal data. Maybe that's not great. So to even start thinking about how to address this problem, we need to be able to put some kind of boundaries around code that we're reusing. And that is one of the fundamental things that Cherry was designed to be able to do. So it's not really a surprise that Cherry is a good fit for this kind of thing. Compartmentalization is all about mitigating unknown vulnerabilities, and several people talked about compartmentalization this morning. The important difference between things like memory safety and things like compartmentalization is when you're thinking about memory safety, enforcing bounds, enforcing lifetimes, you understand what the vulnerability class is, and you're trying to prevent vulnerabilities of that class being exploited. With compartmentalization, you don't need to think about what the exploit vector is. You just think about what are the powers that an attacker will somehow be able to get. And that could be via a code reuse attack, but it could be just, hey, they own that Git repo that you're pulling all the code from. And they put something bad in there. And because that package you depend on is 2 million lines of C, you didn't audit every line. So what is a compartment? Well, at the very high level, it's some code, it's some data, it might be some threads of execution. We know how to isolate those. We have processes, and we've been doing isolation for a really long time. All modern systems, except tiny microcontrollers, come with MMUs, and these are linear descendants of things that were designed to allow you to consolidate a bunch of mini computers into a single mainframe. And so they're really good at isolation. They're not that great at sharing. And this is something that I repeat to everyone I talk to about Cherry. We really know how to isolate bits of code. At the worst case, we run each program on a separate computer. And in a bunch of cases, we do that, and it's fine. Maybe we need more computers, but we all have shares in NVIDIA and AMD these days, so it's great. But if you want to isolate every single library and every single program you're running, putting each one on a different computer actually starts to get expensive, even if you're Microsoft or Facebook. And especially, you need to be able to communicate between these things. And that means you need fine-grained sharing. And you need to be able to reason about what it is that you're sharing. And this is where Cherry really shines, because everything where you're communicating between compartments, whether that's a control flow transition when you're jumping somewhere else, or whether it's just directly accessing shared memory, that has to come via a capability that either was provisioned to your compartment at initial load time, and so is a static thing you can reason about, or which happened dynamically, and it can only happen dynamically by something else passing you a capability via something that you have exposed as an entry point into your compartment, or by a return value from something else that you invoked in another compartment. And that holds for things that you call because they have to be sentries or something else built on top of ceiling to provide a call gate mechanism. And it holds for low-level things like access to memory mapped I/O regions, and higher-level things like here is an object graph that I can now access. And for most of the rest of the 10 minutes I have left, I'm going to talk about Chariot because I'm obsessed. But one of the things that we were trying to do with Chariot is provide an exemplar platform for what you can build if you can assume that you have Cherry support. And a lot of the stuff that's happened in Cherry BSD has been starting on the assumption that you have to support 30,000 packages that were designed before you had Cherry. For Cherry, we expect you to port your code to run on a Cherry platform. We expect the kernel to be aware of Cherry, the compartmentalization model, and so on, to all be layered on top. And so we start with the same foundational guarantees that you'd expect from any Cherry platform with slightly stronger temporal safety guarantees. And then we build a compartmentalization model into the programming model. And then we build operational security on top of auditing for that compartmentalization model. And one of the things that I think really sets Cherry apart from any other technology that I've reviewed is the sealing mechanism. And this is absolutely fundamental to compartmentalization. And we use this to build any kind of software-defined capability. So the sort of thing that will be a file descriptor on Unix systems or a file handle on Windows, but not just from a kernel, from any other two libraries where you want to say, here is some opaque type, and I want to give you a handle to it, and I want you to be able to give it back to me, and I have strong type safety guarantees about that. And we use this for bootstrapping in Chariot because we can bake objects into the firmware image that are only reachable via sealed capabilities from other compartments. And so if you want to be able to allocate memory, you have to have a capability to an allocator quota object, which you then use as your malloc capability. When you call malloc, you pass that sealed capability in. Malloc owns the associated permit unseal capability, so it can turn that sealed capability into a thing that is just a normal pointer that it can dereference. It can subtract from that quota when you allocate memory, add to that quota when you deallocate memory. And now that you have a malloc capability, you can allocate new sealed objects, capabilities to seal capabilities to new objects. And now you can build things like capabilities that authorize sending or receiving messages over a message queue, capabilities that encapsulate a socket, seal capabilities that authorize you to do arbitrary other actions from whatever libraries you're linking in. And this is a very powerful abstraction when you start to think about auditing. So when you link a firmware image with Chariot, and for a more Unix-like system, this would have to be a bit more dynamic. But we're very fortunate because we link all the code that goes into the firmware image together at a single point. As well as getting a binary out of your linking process, you also get a massive JSON document. And this is usually slightly bigger than the linked binary. And it includes the hashes of the code and data that are going in. It includes for every compartment, what functions does it export, which functions does it import, and where does it import them from, which memory mapped IO regions do you have direct access to, which sealed objects, like the ones I was just talking about, do you have access to, how many threads do you have, how big stacks do they have, how big trusted stacks do they have for cross-compartment calls, and where do the threads start running, so you can build a full reachability graph for each thread. And we're not expecting you to look at this JSON document in Vim and go, yeah, that definitely is what my compartmentalization policy said it should be doing. Awesome. We have tooling for that. And sadly, I didn't get to invent a new language, which is like one of my 3 favorite things to do. The Open Policy Agent project has a language called Rego, which is, I mean, imagine if someone thought, I really like Prolog, but I also like Python, and I like JavaScript too. I'm going to make a language. And then you end up with Rego. So it's mostly declarative. And it's designed to consume JSON documents and produce some JSON output. And often that JSON output is just a Boolean saying, yes, complies with policy, no, doesn't comply with policy. But it also has a notion of modules, so you can build reusable components. And so this gives us an auditing flow where firmware authors can write policies that express their intentions for what individual third-party components should be able to do. And the Chariot audit tool can then check your firmware image against that policy. And you can also use this for introspection. And we have a demo outside showing some of that on top of our somewhat alpha quality network stack. So the network stack is, as is traditional, using what Robert refers to as the vacuum cleaner model of software development, created by pointing our vacuum cleaner at the internet and getting a load of code and just wrapping it up in some compartmentalization-friendly interfaces. So all of these compartments are almost entirely third-party code. And this is all unmodified code. We've wrapped it in compartment-friendly interfaces, but we haven't changed any of their code. Of the code in the network stack, 3% is ours and 97% is stuff we got from the internet. So it is a rich source of supply chain vulnerabilities for a sufficiently motivated attacker. And we have things in the policy that say, for example, the firewall component that we've written is allowed to access the network device directly, but nothing else can. And if anything else has a capability to the firewall device, policy fails. Similarly, the API that the TCP/IP compartment has, which allows you to inject Ethernet frames, that should probably only be callable from the firewall. And again, if anything else tries to call it, policy fails. And as I said, we can use this for introspection. So we can say, tell me where the capabilities that authorize creating a socket or adding an endpoint to a UDP socket are and what they authorize. And then we get a nice, pretty printed output saying exactly which compartments are allowed to establish network connections. And we can combine that with some of the which things are allowed to call which functions bits to say, oh, and by the way, this must be a TLS connection because we're not allowed to talk directly to the TCP/IP stack from here. We're only allowed to talk to it via the TLS one. So this lets us now reason about what an attacker can do if they inject a supply chain vulnerability somewhere into our code. If someone looks at the TCP/IP stack that we stole from FreeRTOS and they manage to sneak a supply chain attack in there, what can they do? Well, they can't arbitrarily call user code. They can't allocate memory beyond the quota that we've given to that stack, which currently is way too high. They can't arbitrarily control the firewall. They can probably trick the firewall into adding some rules by lying about DNS responses, but we have plans to fix that. They can tamper with packets going to or from the network, but an attacker on the network can do that as well. So they haven't gained very much power. And over time, we expect to shrink what they can do even more. And we can reason about that. So just to sum up, we like to talk about Cherry as a memory safety thing because fixing 70% of exploitable vulnerabilities, that's nice. That's not a bad thing, but it's the start. Once you can rely on memory safety, you can start building things that have much higher level and much higher value security properties. And Cherry's memory safety is really the only game in town as a building block for this kind of compartmentalization, because it's the only thing that is robust in the presence of an attacker who can give you arbitrary inline assembly in that enormous pile of C code that you're ingesting because rewriting everything on the internet is too much work. And no one wanted to give me $100 trillion when I asked for it. And that then means you can start building supply chain security. As long as you have that memory safety, you have that sealing mechanism, and you have a system designed to take advantage of it. And Simon is glaring at me, so I'm going to stop talking now.
Thank you. Thank you very much, David. We don't really have a time question, but maybe we could slip one in. Is there one question? It's a question that I swap slides over. Stunned silence. Okay.
Sorry.
Oh, yes. Manu.
Yeah,
100%. Literally nothing useful can be built on top of that format.
Let's just say we're talking about it. Okay. Yeah, I mean, obviously, Cherry.ats had a huge influence. We do want to make sure that it ends up as part of the standard. But one of the challenges we have with standard is whatever we put in the standard has really got to work across 32-bit and 64-bit Cherry RISC-V. And that's where it gets slightly tricky. Anyway, without further ado, and I should also apologize, we do have 4 excellent speakers in this. Thank you for pointing out that I couldn't count earlier.